the other day we talked about average value of a function. Okay, and we said that the average value of a function was 1 over b minus a times the integral from a to b of the function. And what we said, I even gave you a problem where we said, let's find one place where that occurs. Well, here's what the mean value theorem says. The mean value theorem is actually directly related to the average value. The mean value theorem guarantees there is at least one point C in A to B such that f of c equals 1 over b minus a, in other words, the average value. So in essence, the mean value theorem is just an extension of the average value of a function. If you can remember one, you can definitely remember the other. But the key is this idea of there being a point C such that f of c is equal to the average value. Okay, that's what the mean value theorem says. And with my experience in grading some previous AP exams, a lot of times you just have to remember this. You've got to remember that f of c equals that 1 over b minus a times the integral from a to b. All right? So it guarantees that there is one place that that's true. Now what I'd like to do is come back to the problem we did the other day when we worked with 4 minus x squared. All right, we had my function was 4 minus x squared, and we were working from 0 to 3. Okay? And the first thing we did was we found the average value, right? We did 1 over 3 minus 0 of the integral from 0 to 3 of 4 minus x squared dx. Now, what did we find that average value to be?
It was like 1. Oh, no, 3.
Wasn't it 3? So this part was 3, and then we had to multiply it by 1/3, and we got 1. Okay? So what the mean value theorem says is there is at least one place in this interval. There is at least one value c that when I plug it into the function, I will get 1. So what we do is we set 4 minus x squared equal to 1, all right, and subtract 4 from both sides. Negative x squared equals negative 3, so x squared equals 3, so x equals the plus or minus the square root of 3. So if you remember, the square root of 3, isn't it in between 0 and 3? Right? So guess what? We have verified there is one place. Okay, remember what the mean value theorem says. F of c equals 1 over b minus a times the integral from a to b of my function, which in this case, I'll just write the general form. Okay, we found this out to be 1, and we also said if I do f of the square root of 3, I will get 1. All right? That's what the mean value theorem says. It says that there is exactly one, there's at least one point where that is true. All right? And that's the idea of the mean value theorem. All right, we're going to change gears now. And we're going to start talking about the fundamental theorem of calculus, which we have to get to. The fundamental theorem of calculus was the great discovery of Sir Isaac Newton and another guy whose name was Leibniz. And this was, when it came to discovering all the things that Isaac Newton did with physics, when he discovered the calculus, he found a way to mathematically explain everything that he was seeing in terms of physics. And that's why the discovery of calculus was so incredible, because he was all of a sudden able to explain mathematically all the stuff he was observing in the real world. Here's what part 1, and by the way, I abbreviate this as FTC, okay, the fundamental theorem of calculus. Part 1 of the fundamental theorem of calculus says that if f is continuous on A to B, then the function capital F of x equal to the integral from a to x of f of t dt has a derivative at every point in A to B, and dot, 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 dot. I'm going to give you the hitch pin on the next page. And and here we go. Very importantly, the derivative of capital F of x. Okay, no, I'm just continuing what I'm saying here, is equal to the derivative of the integral and that derivative of the integral is just f of x. Now, there's some things I want to point out to you about this that are very important. This great discovery by Newton related derivatives and integrals. Look what we're doing. We're taking the derivative of an integral. Now, didn't we say an integral is going backwards? So if I take the derivative of something that's going backwards, don't I wind up where I started? Okay? So look what we have. This statement says that if I take the derivative of the integral of a function, it's just the function at the top limit of integration, or which in this case is x. All right? So in other words, let me kind of summarize this. This just says the derivative of the integral of a function is equal to the function with this little sidebar at the top limit of integration. And like I told you, that must be an x. So, real quick example using this fundamental theorem of calculus. Just a very basic example. Let's, number one, let's find dy dx if y equals the integral from negative pi to x of the cosine of t dt. Well, to find dy dx, isn't that finding the derivative? Right? So if I want to find dy dx, dy dx is the derivative of the integral. Okay, found it because y was equal to they defined the function y as the integral of cosine. So if I want to take the derivative of it, according to the fundamental theorem of calculus, this is just the cosine of x. Okay? So let's do another one. And it's that simple. Okay? We have to just accept the fact that if I take the derivative of an integral of the function, it's just the function at the top limit of integration. Okay? And that's the basic understanding of the fundamental theorem of calculus. Let's do another one. What if I wanted to find dy dx of this one? Y equals the integral from 0 to x of 1 over 1 plus t squared dt. Well, what did we say? The derivative, if I want to find dy dx, that's the derivative of the integral. And if I'm doing the derivative of the integral of the function, it's just going to be the function at the top limit. So it's going to be 1 over 1 plus x squared. Okay? Boom. Now, what if I had this? Y equals the integral from 1 to x squared of cosine of t dt. Well, almost. Now, it is going to be, all right, if I'm finding the derivative, remember, what we're doing, we were asked to find the derivative, dy dx. So I am doing the derivative of an integral. So I am going to have the cosine of x squared. But, remember what I told you, that top limit needed to be an x? It's not just an x, so what we have to do is the chain rule. Okay? We have to do the chain rule of this thing. All right? So, what we do is the derivative of the outside is my cosine of x squared, right? Times the derivative of x squared. It's supposed to be an x squared. So what is the derivative of x squared? 2x. So my final answer is 2x cosine of x squared. All right? So if that top limit of integration is not just an x, if it's an x squared, if it's a 4x, okay, then we have to do the chain rule. I'm trying to get you several examples here so that you're ready to go for homework. What if y equals the integral from x to 5 of 3t sine of t dt. Very good. We learned those rules of integration that says I can switch the limits of integration if I put a negative in front of it, right? So if I want to find dy dx, I need to think of this as the negative from 5 to x of 3t sine of t dt, and I'm finding the derivative of that. The derivative of the integral is just going to be the function now at the top limit of integration. So it's going to, but don't forget our negative here. So it's going to be negative 3x sine of x. Okay? Doing good so far. Now, how about this next one? The integral, let's say that y equals the integral from 2x to x squared of 1 over 2 plus e to the t dt. Now, this is a case where we need, that's why I'm here, I guess, is to help give you some guidance. We need to use the additivity rule. The one that I covered the other day when we were doing our rules of integrals. The additivity rule says that the integral from 0 to x squared is the same thing as the integral from 0 to 2x plus the integral from 2x to x squared. Okay? And that's just breaking it up into the additivity rule. And then, if I know that, then I can, solve for what I want, all right, once I know the additivity rule. So if we look at my original problem, the original problem was dealing with an integral from 2x to x squared. So if I look at this additivity rule statement that I made down here, I see that I've got an integral right here from 2x to x squared. So what I want to do is solve for that to get a new expression. So what I'm going to do is I'm going to subtract this integral right here, the one that's from 0 to 2x. I'm going to subtract from both sides the integral from 0 to 2x. So it will go away on this side. And what I'm going to have is I'm going to have a new expression that has the integral from 0 to x squared minus the integral from 0 to 2x. That's going to be equal to the integral from 2x to x squared. Okay? And so now that I've now rewritten this as this. Okay, I've written it as two separate integrals. So now what I've got is I can now finish the problem. Now I can put in my function and make this the integral from 0 to x squared of 1 over 2 plus e to the t dt minus the integral from 0 to 2x of 1 over 2 plus e to the t dt. All right? And our whole point was to find, remember we were supposed to find dy dx. Well, we did all of that just to rewrite y. So now I can find dy dx by taking the derivative of each of these integrals. I can do the derivative of this integral and the derivative of this integral. So when we do the derivative of the integral, is just going to be the function at the top limit of integration, which will be 1 over 2 plus e to the x squared, but since I have an x squared up here, I need to do the chain rule, so that will be times 2x minus, for this one, it will be 1 over 2 plus e to the 2x. Once again, that's not just an x, so I need to do the chain rule, so it will be times 2. And the simplified version of that would be 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So once again, the most important thing that we did on this problem is if you see a situation where the bottom limit has an x and the top limit has some kind of x, you need to use the additivity rule and then solve for the expression that we started with. All right? And once you get there, once you have that new expression, then you can plug in your function and actually start doing the fundamental theorem of calculus. And we will stop there for today.